concept video for harmonic motion, and we're going to discuss unforced harmonic motion, and we'll get into what that means a little bit later. So harmonic motion is just the application of second order linear differential equations, which is what you've been studying. So mainly this is used in problems involving physics, physics involving springs or any other oscillating system. So in physics we have Newton's second law, F equals ma, or the net force on an object equals the object's mass times its acceleration. So the acceleration is just the second derivative of position, which we'll just call y in this case. So this is what acceleration is, and the net force on a spring is usually proportional to the position of the object from the spring. So, or sorry, from its equilibrium position. So if we have a spring, we have an object with a mass m, and we take this and we move it a distance y. We see that the object feels a force in this direction. So we'll call this the force of the spring. So this is the force of the spring. We have a negative sign because it's always pointing the opposite direction from the position. And K is just a constant, which we call the spring constant, or the stiffness. And we usually have a thing called a damping term, which is proportional to the velocity, and it slows your object down. So again, we have a constant, we'll call this the damping constant, mu, and this is times the velocity. The velocity is just the derivative of your position with respect to time. So rewriting this, we get negative ky minus, and this minus sign means that the damping force is always opposite of your velocity, so it's always slowing you down. So anyway, we get negative ky minus mu y prime equals m y double prime. Adding everything over to the other side, we get m y double prime plus mu y prime plus ky equals 0, and this is just the kind of differential equation we've been dealing with. If we divide everything by m, we put it into a more simple form. So the reason we call this unforced is that we don't have anything on this side of the equation. That would correspond to, let's say, some external force acting on this system. So let's say we were pulling the spring as well. We'll call this F pull. Well, then our net force would include this F pull, which would follow us through. So we'd have F pull over here, and then ultimately we would have F pull on this side of the equation. We don't know how to deal with this yet, so we will just consider the case where this is equal to 0. There's no external force. So we can go ahead and take a look at this solution, so this equation. First we can consider another example of where this comes into play. This comes into play when we discuss circuits. For circuits, we have the quantity called charge, and charge moves around in the circuit. So if we have a circuit with a resistor and a capacitor and an inductor, which has an inductance L, the capacitor has a capacitance C, and the resistor has a resistance R. The behavior of the circuit follows this differential equation if we use if we add up the voltages around the circuit, and that's going to be L times the change in current L di dt equals negative R times I, so that's just Ohm's law, minus Q over C. And if we note that current is just a time derivative of charge, we find that this is what this equation simplifies to. It's going to be L times Q double prime plus R Q prime plus 1 over C times Q equals 0. And that's pretty much the same equation we have over here. Of course, we can divide everything by L. So these are pretty similar equations. So both of these physical situations follow harmonic motion. But let's deal with what we've been looking at, this one, the spring. So we can introduce some new constants. There's a constant called omega naught, which is the frequency of the system. And that's defined to be square root of k over m. And then we define this constant c to be mu over 2m. So that makes this equation, we rewrite this as y double prime plus 2cy prime plus omega naught squared y equals 0. So our first case is where c equals 0, and this is called simple harmonic motion. And that implies that there is no damping. So when there's no damping, the equation looks like this: y double prime plus omega naught squared y equals 0. This has the characteristic equation lambda squared plus omega naught squared equals 0. So lambda equals plus or minus I omega naught, which gives us the solution y of t equals a cosine omega naught t plus b sine omega naught t, where a and b are just arbitrary constants. So this we can define a to be the amplitude times the cosine of this quantity phi, which is called a phase angle, and b to be b is capital A, so the amplitude times the sine of this phase angle. That means we can rewrite y of t as a cosine phi cosine omega naught t plus a sine phi sine omega naught t. If we factor out a and use the cosine addition formula, this simplifies to a cosine omega naught t minus the phase angle. So a is the amplitude of this cosine function. It's just how high this goes. And the phase angle is, since cosine starts at the peak, it's the distance this wave is shifted on the time axis, if this is the y-axis.